and this is my science fair project on radioactive half-lives, measuring the effect of time and environmental variables on metastable barium-137. This is my abstract. It's a basic overview of my project, and pretty much what I'll be going over in this presentation. The purpose of this investigation is to measure the radioactive effects of nuclear decay on metastable barium-137. My hypothesis can be broken down into two main parts. If an eluting solution is run through an isotope generator, producing barium-137, that barium-137 will decay at a constant rate, and if the barium-137 solution is exposed to extreme environmental factors, it will continue to decay at said rate without changing the rate of decay. There was a lot of research that went into this experiment involving nuclear radiation, calculating half-lives, looking at the various variables that I'll be exposing my solution to, as well as real-world applications for radioactive isotopes, considering they're a huge part of medicine and science. The isotope generator that I used in this project is basically cesium inside a resin ball that is decayed into barium-137 before being drained out of the isotope generator using an eluting solution. The solution draws the barium-137 onto a shallow planchet, and then it can be monitored using a radiation monitor. The radiation monitor was suspended above the solution planchet using clamps, and the variables that I tested, excluding the no variable tests, were ultraviolet light, a rare earth magnet, and dry ice. I used a data collection program called LoggerPro to collect the radiation count every half minute and store it on a data spreadsheet. Here are a couple of setups for my radiation monitor and the various variables that they were testing. Here you can see the data spreadsheet, and in order to collect the most accurate results possible, the first 15 minutes of data were utilized. That way background radiation and cesium-137 in the sample wouldn't be an issue. Data organized onto data tables could then be used to calculate the half-life of each sample using the integrated rate law for first-order reactions. Basically, I took the natural log of each data point and created a slope for each set of data. That slope could then be plugged into the formula and solved for half-life, and I would have the half-life for each sample. On the left, you will see a graph of the original data, which is a radiation count over time, and on the right you can see the natural log over time for each radiation set, and I was able to use the rate graph to calculate the half-life. Here are a couple of very important data points for each set of data, each environmental factor. I was able to draw a lot of conclusions using these values, and it gives you a basic idea of how I calculated each data set. Conclusions I drew from the calculations that I did regarding half-life included the average half-life for each solution was extremely similar to the no variable solution or the original untested solution, and the only statistical differentiation in comparison to the no variable tests was with the dry ice samples, but looking at the tests, it was concluded that it wasn't an issue in decay rate, but rather an issue in testing that led to the statistical difference and really did not affect my hypothesis overall. Discussion points for this test, or these series of tests. The results of the experiment are completely supported by all published work done on the topic of half-lives, and extending half-life is extremely difficult. There are several theorized ways to do so, but most involve either time dilation and relativity, or extremely complex pieces of equipment like particle accelerators. And the results of this experiment completely address both the original research question as well as the hypothesis of this project, and the half-life did not really change when introduced to the variables supporting the hypothesis.